Welcome back, everyone, to another college algebra lecture. Today, we are going to talk about rational functions. And this lecture is actually going to be split into two parts. There are a lot of different pieces and details when it comes to rational functions to cover, and I didn't want to squeeze it all into one lecture. So today, we are going to talk about 5 different properties. Next class, I'll introduce 2 more properties, and then we'll bring it all together and how you can use all properties to graph rational functions. So let's get started. Now, rational functions, we have dealt with rationals before when we solved them in terms of equations, but we didn't deal with them as functions. So we're going to begin by talking about the definition of a rational function, which is a function f of x that's of the form p of x divided by q of x. Now, here, both p of x and q of x are going to be polynomial functions, and this is really just a fancy way of saying that a rational function is a fraction that has x in the denominator. That's it. So anytime you see a fraction that looks like it has x in the denominator, you're dealing with a rational function. All right, so the first property we're going to deal with is how you can determine the domain of a rational function. And this is something we have already covered in this class when we talked about the domain of functions. And we're just going to cover it again right now just to make sure everyone remembers what to do. Okay, so since we are dealing with fractions that have x in the bottom, the only thing that we are going to concern ourselves with is making sure that the denominator never equals 0. Because if we divide by 0, world blows up, we're all dead. So if we're going to find the domain of a rational function, we got to determine what x values cause us to divide by 0, and then make sure we exclude them. Now, I went ahead and typed up the steps on what to do. The first thing we're always going to do is factor the numerator and denominator. That's going to make things easier for us when it comes to finding zeros. And then to determine the denominator, you're going to set the denominator not equal to 0, so the equal of the line through it, and then solve for x. Those x values are going to be the x values that we exclude from the domain. Okay, so looking at the first one right here, if I want to find the domain of this one, all I have to do is first see if I need a factor. Neither of these need to be factored. Then I can set the denominator not equal to 0. So x plus 4 does not equal 0. Now solving this for x, I get x does not equal -4. That is the only x value that I have to exclude from my domain. Because if I were to substitute -4 in for x up here, -4 plus 4 is 0. I divide by 0, nothing works out. So this is the number we have to exclude. To write this up in proper math language, we're going to do it in set notation. So I do the set, which is the curly brackets, of x's, such that means we do a bar, x does not equal -4. That's what we're going to do for the domain. You could have done interval notation with the parentheses and brackets, but anytime you have to exclude more than one thing, it gets kind of ugly. So this is what we'll use. And that's it. That's all you have to do for determining the domain. Set the denominator not equal to 0, solve for x, and then write it in proper notation. Now, if you're good to go after that one, please feel free to skip ahead, but I have more examples that might be useful for you later. So looking at B, I don't need to factor the numerator, but I can factor the denominator using the ABC method. So rewriting this is going to be 8x plus 9 divided by, using the ABC method that I have shown several times, our A times C is 21, our B is 10. The factors of 21 that add up to 10 are 3 and 7. And if you still want to do the little factor trio on the side for the A times C, go for it. There's nothing wrong with that. So I have x plus 3 and then x plus 7. Now, the reason I want to factor first is because knowing that I have to set the denominator not equal to 0, when it's factored like this, we can solve it really fast. Looking at this one, I see that x cannot equal -3, looking at this next one, I get x cannot equal -7. And we have our numbers. So to write this up in proper notation, I say that set of x's such that x does not equal -3, comma, x does not equal -7. That's it. That's all you got to do. All right. Now for the next one. So right here, I see I can factor the top. So I'm going to do that real quick. I can take an x out of both. So I have x and then x plus 7. Now on the bottom, I see that I can factor a 2 out of everything. Now, since I have to factor 2 out, that's going to change my coefficients. So before I do the ABC method, I'm going to rewrite this, that's a 4, minus 21. Okay, now doing the ABC method is going to be a little bit easier down here. A times C is -21, my B is 4. The two numbers that I can use right here are -3 and +7. So rewriting this again, I have 2 over x, or I have x times x plus 7 divided by 2, and then x minus 3, x plus 7. Got it. Now solving these, this 2 doesn't have an x attached to it, so doesn't affect us. I get x cannot equal 3, and then x cannot equal -7. Got it. So writing out our domain, we have the set of x's such that x does not equal 3 and x does not equal -7. All done. Nothing else to do. All right, now for the last one. So for this last one, I have x squared minus 4 divided by 3x squared minus x minus 10. Up here, I can factor that. This is a difference of squares. So the difference of squares, we know that's going to be equal to x minus a times x plus a. Or if remembering the difference of squares doesn't work well for you, remember, you can do the ABC method on this. The only thing you got to remember is your b is 0, because that's the term that's missing in the middle. So I know I can factor this one. That's going to be x plus 2, x minus 2. Now for the bottom part, this one, I'm going to need to use my ABC method, but my a does not equal 1. So I'm going to have to remember how to do the divide and swing stuff. That I will write over here on the side just to make it a little bit easy for us. And just to kind of help you out, I will show you the steps on this one. So right here, our a times c was -4. Our b was 0. That gave us -2 and 2. Got it. Now right here, our a is equal to 3. A times c is -30. Our b is -1. The numbers that I can use right here are 5 and -6. Cool. Now I'm going to go ahead and keep working over here on the side. I have x plus 5 and then x minus 6. We have to remember to do the divide and swing. So I'm going to divide by my leading coefficient, 3. This doesn't reduce, so that's going to give me 3x minus 5. This does reduce. That's going to give me x minus 2. That's plus 5, sorry. Got it. So right here, I have 3x plus 5, and this one is x minus 2. So never feel bad about having to do a little bit of side work. Now, figuring out what my domain is, I see for this one, if I do -5 divided by 3, I cannot equal -5 over 3. And for this one, I cannot equal 2. All done. So my domain for this one is a set of x's such that x does not equal -5 over 3, and x does not equal 2. All done. So we have found the domain of these functions. Nothing too crazy, and it's stuff that we've done before. Okay, so the next thing we're going to talk about is how you can write your function in lowest terms. And what I want to draw your attention to before I turn the page is these last two problems right here. When you are looking at the factored versions right here, or I guess I should say right here, are they fully reduced? Hopefully you're noticing that they're not. Right here, the numerator and denominator both have x plus 7 as a factor. And over here, the numerator and denominator both have x minus 2 as a factor. So I could effectively reduce this fraction and make it a little bit smaller. That's what we're about to do when we write it in lowest terms. Look for what's the same after you factor them and reduce. But as a warning, this goes up here to this one and it's on the next page too. Always determine your domain before you write your function in lowest terms. The reason we have to do that is because looking at both of these, I see for my domain I have to exclude -7, but once I reduce, that would have gone away. So just be warned, and I'll mention it again on the next page. All right, so lowest terms. This is just reducing your function by canceling out factors on the top and bottom that are the same. That's it. I gave you the steps on how to do this yet again. Step 1, factor. Step 2, reduce. That's it. And then again, I gave the same exact warning. Always determine the domain before you reduce. All right. So again, I'm going to do all the examples, but if you don't feel like you need all of them, please feel free to skip ahead after doing a couple. So looking at this first one, I'm going to factor. Up top, I see I can take a 2x out. So I have 2x on the outside. What's left over is x plus 4. And for the denominator, I can use the ABC method. So for this, I see the numbers I can use are x plus 1 and x plus 4. Got it. Now, just so we can keep our skills fresh, every time I do this, I want to list out the domain. And I'm not going to do the set version. I'm just going to write it out briefly. The numbers I cannot equal for x, looking right here, I cannot equal -1. And looking right here, I cannot equal -4. Always list those out because once we get to the bigger problems, having this ahead of time will make things a little bit easier, especially even on the next page. All right, so we have our domain, we have this factored. Now let's write it in lowest terms. So for lowest terms, I see that I have x plus 4 as a factor in the numerator and denominator. So I'm going to cross that out. That means what's left over is 2x over x plus 1. Done. That's all you got to do. Now, I do want to get you in the habit of doing one extra little step, which is very easy, but it's going to help us out on the next page. Look over here. I see that x plus 4 completely disappeared out of my denominator. I'm going to put just a little bitty x underneath the -4 because when I remove this, the -4 went with it. I still can't have it in my domain, but something special happens with the ones that get crossed out. So anytime you cross something out and it disappears completely, put a little -x or put a little x under it. That way we know something happened. All right, that's it. That's the lowest terms. So let's keep going. If you feel like you got it after that one, feel free to skip ahead. Otherwise, I'm going to do some more examples. Looking at this one, I see that I can factor 5 out. That leaves me with x minus 2. For my denominator, doing the ABC method, I see the two numbers that I need are going to be -2 and +7. Oh, no, not +7, -7. My bad. All right, so we got -7. Now, as far as the numbers that I cannot equal, x cannot be +2 and +7. Got it. Now writing this in lowest terms, the factors that are the same on top and bottom are x minus 2. So now I'm left over with 5 over x minus 7. Got it. And now that's my final answer, but so we can get to the habit. The negative 2 disappeared completely, so I'm going to put just a little x under there to say that I got removed. Done. All right. Now for C, I'm going to need to do the ABC method on both. A times C is negative 15. My B is negative 2. So I see the numbers that I need are positive 3 and negative 5. So I have x plus 3, x minus 5. Down here, this is going to be A times C is negative 20. My B is negative 1. The numbers I need are positive 4 and negative 5. Got it. Now listing out my domain, the numbers I know x cannot equal. Looking right here is negative 4, and right here, positive 5. Got it. Now, reducing, I see that they both have x minus 5. So my lowest terms will be x plus 3 over x plus 4. And as far as the one that disappeared completely, the 5 was removed. Perfect. Now for the last one. So looking at this is another difference of squares. You can identify them by having a square minus another square. 3 squared is 9, so I know that's a square. Or do the ABC method with your b being 0. So I know I can go ahead and factor the numerator. That's going to be x minus 3, x plus 3. For my denominator, I see that I can take a 2x out of everything. Now, before I do the ABC method, it's going to be a lot easier if I write it down factored first, so I can get a good idea what my a times c will be. So that's going to be x squared plus 6x plus 9. Okay, so now I can do my ABC method. A times c is 9, my b is 6, so my factors of 9 that add together to be 6 are 3 and 3. So now I have x minus 3, x plus 3, divided by 2x, x plus 3, x plus 3. As far as the numbers I cannot equal, x cannot be negative 3. See that right there? Negative 3 again, so I don't need to put it twice. Right here, anytime it's just x and the number in front, then I can set it equal to 0. Divide by 2, I still get 0. Cool. So now I can reduce. Well, I see x plus 3 is the same on top and bottom, but there's 2 on bottom. I know it's tempting to go ahead and cross them both out, but you can only cross out 1 for 1. There's 1 on top, so 1 on bottom. So my lowest terms right here, I have x minus 3 divided by 2x, x plus 3. As far as anything else that needs to be removed over here, well, I see 0 still needs to be included. And I know we crossed out x plus 3, but there's still an x plus 3 there. So neither of these get removed. Only put a little x under it if it completely disappears from the denominator. Only if it's completely removed. All right, so now you should be comfortable with finding the domain and how to write your function in lowest terms. All right, so at this point, I kind of want to give you an idea of what's coming up next. What we're about to do is we're going to talk about what happens to our graph at these values that we have to remove. So right here, looking at this one, I see that The two x values that I cannot equal are -4 and 5. I know something bad happens right there. I divide by 0, they're an error, I can't have that. But graphically, what is going on? Well, two different things happen, and it depends on whether it gets removed or whether it stays. So let's take a look at the graph and see what it looks like. So looking at this one, I have x squared minus 2x minus 15 divided by x squared minus x, minus 20. So this is my rational function. And just to kind of show you that I cannot have -4 and 5, at -4, I get an error. And at 5, I still get an error. So something special happens, that's why I cannot equal them. But looking at the graph, right here at -4, I see my graph splits. I have one side, or I have the left side, and then the right side. So something happened, it broke it up. And then here at 5, I don't have that anymore. Well, what's going on is there is a vertical asymptote here at -4. The reason we get a vertical asymptote is after we write this in lowest terms, -4 is still an issue. So after reducing, if a number is still an issue, it's going to cause a big issue for our graph, causing it to split up. But 5, that got removed. It's still an issue for the original, but it's no longer an issue for the lowest terms. So something else special happens that we're going to get to in a couple of pages. But what we're about to talk about now are the vertical asymptotes, what make our graphs split up. Those occur anytime a number is still an issue for lowest terms. And bam, here we go. Vertical asymptotes. So first off, vertical, that just means up and down. And asymptote, that is a line that your graph will follow. So an asymptote is a line that our graph will follow. Looking right here, I see that my graph goes up on both sides. It follows the dotted line, or one side goes up, one side goes down. But either way, it's following the dotted line. That's what a vertical asymptote is. It's a line that goes up and down that our graph follows. But one thing that's special, and this is only for vertical asymptotes, it will never cross. So our graph will never cross this dotted line. Think about it as a fence. Your graph is heading towards it, but it cannot cross, so it has to either shoot up or down to avoid it. All right, now I put some extra stuff in here about the multiplicity. That's not anything I'm ever going to ask you about, so you don't have to read through that. Now, when it comes to locating vertical asymptotes, we've actually done all of the work that is needed to do this. First up, write it in lowest terms. Got it. Once you write it in lowest terms, you're going to set the remaining denominator equal to 0 and solve for x. Those will be your vertical asymptotes. Well, we've already done that by listing out our domain. So let's take a look and see what we can find. Looking at this first one right here, I'm going to have to write it in lowest terms. In order to do that, we need to factor. So factoring the numerator, I see I can take 4x out. So I have 4x. And on the inside, I have x minus 3. Now on the outside, for the denominator, I see I can take 4x again. So I have 4x. What's left over is 2x plus 3. Now again, let's talk about what the domain is. Our domain right here, I know x cannot equal 0. And solving this one, minus 3 divided by 2, negative 3 over 2. Those are the two x values I cannot have. They will cause issue when I graph it, so I know something's going on. Now, let's write this in lowest terms. I see that the 4x can cancel. Removing the 4x, I have my lowest terms right here. X minus 3 divided by 2x plus 3. Got it. Now, this is where putting that little x is going to come in handy for us. Right here, I see that the x was removed, so the 0 got removed. That's cool. Well, the way this helps us on this step is find the vertical asymptote. My vertical asymptote is going to be equal to whatever makes my denominator equal, 0 again. Solving this, minus 3 divided by 2, negative 3 over 2. That's the part of the domain that didn't get crossed out. So whatever does not get removed from your domain, that is your vertical asymptote, because it is still an issue for our lowest terms. And that's the easy way to find this. Factor, get your domain, write it in lowest terms, then you get your vertical asymptote. Guaranteed. So vertical asymptote is still an issue for the lowest terms, and that's the one that didn't get crossed out. All right, let's do it again. So right here, factoring this, I see that I can take out 7x, and then I'll have x plus 3 left over. For the denominator, I see that I can take an x out. Now I'm going to have something I can do the ABC method with. I have x plus 3, x plus 3. Perfect. The numbers that I cannot equal 0, and I cannot equal negative 3. All done. Now, next up, lowest terms. Writing this in lowest terms, I can cancel out an x and an x, so the 0 is removed. I can reduce the x plus 3. I can take away just a single x plus 3. But right here, since this is still included in the denominator, I'm still going to keep it over here. So for my lowest terms, I have 7 over x plus 3. Now, figuring out my vertical asymptote, the one that didn't get removed is x plus 3. Or, sorry, x plus 3. Yeah, x plus 3 didn't get removed. And the negative 3 is my vertical asymptote. So 2 ways you can do this. Solve the remaining denominator for 0. That gives us negative 3. Or just look to see which one doesn't get crossed out. And that's it. That's how you can find your vertical asymptotes. So again, if you're good, go ahead and skip ahead. But otherwise, I got some more examples for you. Alrighty, looking at C. On this one, I see I can factor the numerator using the ABC method. The numbers I'm going to need to use are positive 2 and negative 5. Got it. And for the denominator, I see that I can take an x out. Once I do, it's the same exact numbers as above. So I can say x plus 2, x minus 5. Perfect. So now I got that going. Listing out my domain, I know x cannot equal 0, x cannot equal negative 2, and x cannot equal 5. Okie dokie. So now, doing our lowest terms, x plus 2 goes away, x minus 5 goes away. Just in case you don't remember, there's still a 1 in front of that parentheses. There's always 1 times everything. So what I'm left with is 1 on top and x on bottom. Now, as far as what got removed, the x plus 2 completely disappeared, so the negative 2 is removed. X minus 5 completely disappeared, so x equals 5 disappeared. So that means my vertical asymptote, x equals 0. And again, that's the one that didn't get removed, or the proper way to think about it, it's still an issue for my lowest terms. Okay, time for the last one. So for this last one right here, I see I can remove an x from everything, and then I can do the ABC method. In the ABC method, I have x minus 1, x minus 9. For my denominator, I see that I can divide everything by 3. So I can take a 3, and then I can get x squared out as well. That's going to give me x squared minus 8x plus 7. Doing the ABC method on this now, I have x minus 1, x minus 9, divided by 3x squared. Do my ABC method on this one, I see that we're going to need -1 and 7. Got it. So now the numbers that I cannot have for x are 0, 1, and 7. Perfect. So now we can go ahead and do our lowest terms. What we can get rid of, then x minus 1 goes away, so I remove 1. Now x and x squared reduce, but I still have an x down here, so that 0 is still there. So for my lowest terms, I have x minus 9 divided by 3x, x minus 7. For our vertical asymptotes, I have x equals 0 and x equals 7. Now, just in case you're wondering why I'm splitting these up instead of saying x equals 0, comma 7, these are actually the equations of a vertical line. If you remember before, the equation of a vertical line is x equals some number. These are separate equations, so they do need to be written separately. And that's it. That is what it looks like. So vertical asymptote, pretty easy to find. Now, you should have a good grasp of how to find the domain and what the domain means to us, how to write it in lowest terms, and now vertical asymptotes. But I'm kind of hoping you're wondering at this point, what's going on with some of these values? What happens whenever we solve a vertical asymptote, but we remove something else? So I want to show you what that looks like. So let's see here, what would be a good one? We'll look at this. So looking right here, I'm going to type in the function. I have x to the third minus 10x squared plus 9x divided by 3x to the fourth minus 24x to the third plus 12x squared. Okay, so it's a little hard to see, but what I want you to notice is right here, when x is 0, my graph splits. I have one on the left side, one on the right side. So I have a vertical asymptote right there. Right here at 7, my graph splits. The left side's going up, the right side's going down. So at 0 and 7, I have a split and I have a split. But right here at 1, the value that got removed, I don't have a split. It's not jumping the same way it did for the asymptotes. But looking at the table, it is still an issue for me. I cannot have x equals 1, but I don't have an asymptote. Well, what we have right now is what are referred to as removable discontinuities. It's still an issue, but it doesn't cause that big of an issue. What they look like are little holes or gaps, just like this. You would have your graph as normal, but at that particular point with the x value that matches whatever value was removed, you're going to have a little open circle. Your graph will continue on either side. Now the cool thing about these, the x value for this point, because it is just a single point, we already know. It's the value that we listed out and removed, the one that has a little x under it. We know the value. The way you find the y value for it is you just take that x and you plug it into the lowest terms. And that's how you find it. So all the work that we've been doing so far, we can now extend it to just one little bitty step to find gaps or removable discontinuities. Different books and different classes call them different things. So far, I've seen them called gaps, holes, and removable discontinuities. Removable discontinuity is the proper term, but the book I'm using while I'm making this lecture calls them gaps, so that's what I'll call them here. Now, yet again, I gave you the steps for all of this. First step, write it in lowest terms. Second step, the eliminated x value will be the x value of the hole or gap. And then to find the y value, substitute it into the lowest terms, and then you can find the y value of the point. And that's it. Not too much extra work from what we have already been doing. All right, so I have several examples on this. Taking a look at the very first one, I'm going to factor as usual. I can factor an x out, and I have x plus 1 left over. On the bottom, doing the ABC method, I see that I can do x plus 1, x plus 4. Got it. Now, doing the domain, the values I can't equal are -1 and -4. Perfect. Now, writing this in lowest terms, the values I see can be removed, x plus 1. So I'm going to put a little x under the -1 because that went with it. Now I have x over x plus 4. As far as the vertical asymptote goes, we can list that out because it's really fast. -4 is still the issue for us. So x equals -4. All done. Now for the gap. For the gap, the x value is the value that got removed up here. So -1. To find the corresponding y value, we're going to take this -1 and substitute it in to the lowest terms. So I have -1 over -1 plus 4. That gives me -1 over 3. It's done. That is the gap. Nothing else to do. So anything that doesn't get eliminated from the domain is a vertical asymptote. Whatever does get eliminated becomes a gap. And you're done. There's nothing else to do. All right, so if you're already great after that one, feel free to skip ahead. If not, I have some more examples for you to help shore you up. So looking at this next one, I need to start by factoring. I can use the ABC method on both the top and the bottom. For the top, the numbers that I wind up needing to use are going to be -2 and +6. For my denominator, the numbers I need are +3 and +6. Okay, finding the domain, I'm going to set each one of these equal to 0. That gives me -3. And that gives me -6. Done. Now for the lowest terms, the number the factor I see disappears, x plus 6. So since it completely disappeared, I'm going to put a little x under the -6. For my lowest terms, I have x minus 2, x plus 3. As far as the vertical asymptotes go, I see that -3 is still an issue. So I have x equals -3. We just learned about all these, and it's taking barely any time to get them. Now for the next one, the gap. Which be warned, you won't always have gaps, but when you do, this is how you find it. The x value will be the x value that got eliminated from the domain, so -6. To find the y value, we just substitute this in up here. So I have -6 minus 2 divided by -6 plus 3. That winds up giving me -8 over -3, which is just 8 over 3. All done. Nothing else to do. All right, now for the next one. For this one, I see that I'm going to need to factor the numerator by 2x to begin with, and that's going to give me x squared minus 4x minus 5. And then for the denominator, I can take x squared out. That's going to give me x squared minus 3x minus 10. Doing the ABC method for both, I have 2x. This one's going to wind up giving me x plus 1, x minus 5. And for my denominator, I have x squared still. This one is going to be x plus 2, x minus 5. Perfect. Now, as far as the numbers I cannot have for x, I see 0, -2, and 5. All right, now for the lowest terms, I see x minus 5 can go, so that gets removed. Here, x goes, but I still have an x on bottom, so that 0 has to remain. So for my lowest terms, I have 2x plus 1 divided by x plus 2. Got it. Now, as far as my vertical asymptotes go, I have x equals 0, because that's still an issue right here, and x equals -2, because that's still an issue right there. For the gap, this one does have one because we had a value removed. The x value is 5. Finding the y value, I have 2 times 5 plus 1 divided by 5 plus 2. Doing this, that's 6 times 2 is 12. That 7 times 5 is 35. That doesn't reduce, so I get 12 over 35. There we go. That's our gap. Nothing else to do on that. Okay, now for the last one. For this, I see that I can factor an x out of the numerator. Once I do that, I can go ahead and do the ABC method. The numbers I see I can use are +3 and +8. For my denominator, I see that I can factor an x out as well. The numbers I get afterwards, I can do the ABC method with, and I wind up getting, let's see here, -2 and +3. Got it. Now, figuring out our domain, the x values we cannot equal, 0, 2, and -3. Got it. Now, writing this in lowest terms, I can get rid of x plus 3. So the -3 gets removed. I can get rid of the x, so the 0 gets removed. So in this one, I removed 2 values. So that means I'm going to have 2 gaps. Writing this in lowest terms, I have x plus 8 divided by x minus 2. For the vertical asymptote, I only have one value remaining. That's an issue, and that's going to be 2. Perfect. Now, let's figure out the gaps. For the first one, I know my x value is 0. Then I'll have a y value, and my other one that got removed is -3. Okay, figuring out the y value that goes with it, I have 0 plus 8. When I plug it into the lowest terms, 0 minus 2, 8 over -2 gives me -4. Got it. Now over here, I have -3 plus 8, and then -3 minus 2. When I substitute it in, that's going to give me 5 over -5, which is -1. Perfect. There were 2 gaps on that one. So when I graph this, I will have 2 little open circles and then 1 asymptote. And that's all you need for gaps. And again, remember, not every single rational function will have a gap, but if they do, you now know how to find it. Okie doke. So that's it for some of the new properties for you. I do have one more property to show you, but this one is something you should be kind of familiar with. Intercepts. So the intercepts of a rational function. We know from all of our math training, starting in Algebra 1 going up to now, that intercepts are where our graph crosses an axis. The y-intercept is where we cross the y-axis, and x-intercept is where we cross the x-axis. Now, the way that we're going to find these is we are going to first write it in lowest terms. That is a must. You have to do this in lowest terms before you do anything else. Then, for the x-intercepts, well, the x-intercepts happen where our function equals 0. That's something we've talked about for quite a while now. Well, for our function to equal 0 and it's a fraction, that just means that the numerator needs to be equal to 0 because 0 divided by a number is still 0. So what we do is we set the numerator equal to 0 and then just solve. Because if the numerator is 0, the whole thing's 0. Well, finding the y-intercept, that one's pretty neat to do because for the y-intercept, we are guaranteed to have x equals 0. That's always going to be the case. So for the y-intercept, x equals 0. So that means all we got to do is substitute 0 in for x and solve. All right, so let's get into it. And again, so that you stay fresh on everything we've done so far, we are going to follow all of these same exact steps that we have been doing. So looking at the first one, I see I can do the ABC method for both the top and the bottom. The numbers I need to use here are positive 2 and positive 3. So x plus 2 and x plus 3. For the denominator, the numbers I need to use there are 3 and 9. X plus 3, x plus 9. Doing our domain, I know x cannot equal negative 3 and x cannot equal negative 9. Writing our function in lowest terms, I see that we can remove x plus 3, so that means the negative 3 gets removed. So my lowest term, x plus 2 divided by x plus 9. My vertical asymptote, I get x equals negative 9. And just to go ahead and keep it in our brain, we're not going to do all of it, the gap right here, the x value is negative 3. Got it. Okay, so now for the intercepts. I like to start with the y just because it's the easiest. For the y-intercept, we know guaranteed that the x is 0. So looking right here, I can say 0 plus 2 divided by 0 plus 9 gives me 2 over 9. That's it. That's my y-intercept. 0, comma, 2 over 9. Nothing else to do. Now, as far as the x-intercept goes, the x-intercept happens whenever the numerator of my lowest term is equal to 0. So x plus 2 equals 0. That gives me x equals negative 2. So my x-intercept, negative 2, comma, 0. And that's it. That's all you need for the intercepts. Y-intercept, substitute 0 in for x in the lowest terms. X-intercept, set the numerator of the lowest terms equal to 0 and solve. So that's it. All right, so now, if you're good after that one, don't leave the page. Definitely pay attention to C and D because there's something special for each one. All right, now I'm going to do B real quick. Looking at this one, I see that I can factor. So factoring this one, I have, see here, -1 and +10. So x minus 1, x plus 10, divided by, for the bottom, I see x plus 2, x plus 10. Got it. Now, as far as the numbers we can't equal, I know I can't be -2 or -10. Writing our lowest terms, I can remove 10. So that got removed. Now I have x minus 1 divided by x plus 2. Our vertical asymptote, x equals -2. And for the gap, I have to kind of stack this one. I know the x value is -10. Finding the y value, we know how to do that. We can substitute it in. All right, now for the intercepts. For the y-intercept, I'm going to substitute 0 in up here. So I have 0 minus 1 divided by 0 plus 2. That gives me -1 over 2. So I have 0, comma, -1 over 2. All done. For the x-intercept, I take my numerator, x minus 1, and I set it equal to 0. That gives me 1. So I have 1, comma, 0. And we're done. We just found a ton of information in just a couple of minutes. We can factor, we can determine our domain, we can write it in lowest terms, we can find the vertical asymptote, we can find the gap. We know how to find the y value by substituting the -10 in, find the y-intercept where we cross the y-axis, and we can find the x-intercept where we cross the x-axis. All right, now these last two, they each have something a little special to them that I want to draw your attention to. Okay, so we'll start this off and go through it as normal. I can factor, so I have x, and then doing the ABC method, I see I need +3 and -6. Okay, and then for the denominator, I need to factor out a 3x. What's left over is x plus 4. Got it. Now, determining our domain, I see that x cannot equal 0 and -4. All right, now for our lowest terms, we can get rid of x. So now I have x plus 3 times x minus 6 divided by 3x plus 4. For our vertical asymptote, I see that we're going to have x equals -4. And for the gap, we have 0 being removed because the x went away. So my gap is 0, comma, something. All right, now let's find our intercepts. So for the y-intercept, that happens when x is 0. When x is 0. Hopefully you see what I'm getting at. But just in case you don't, let's go through it. That's going to give me 0 plus 3 times 0 minus 6 divided by 3 times 0 plus 4. That's -18 divided by 12, which is equal to -3 over 2. So you might be thinking, yay, we found the y-intercept. We got it. Well, if you think we found the y-intercept, you are completely wrong. That is not our y-intercept. Because, look right here, our gap happened at the same x value. So, since this is a gap, I do not actually cross the y-intercept. We did some work for nothing. all you have to say is that there's none. This is a gap here. So what you need to be aware of, if you ever are looking for the y-intercept, make sure you check to make sure that you do not have a gap or a vertical asymptote at that value. Because sometimes we do have vertical asymptotes or gaps at x equals 0. Be very cautious. There is no y-intercept here because the gap takes priority. All right, now as far as the x-intercept goes, I'm not going to trick you on this one. We're going to take the numerator of the lowest terms, so x plus 3, x minus 6, set it equals 0 and solve. That gives me x equals -3 and 6. So I have two of them, -3, 0, and 6, 0. Got it. Okay, so that one, there was a little tricky piece. Always keep that in mind. Now for the last one. There's something special here too, but we're going to go about this as normal. So looking at this one, I see I can factor out -3, and that's going to be x plus 3. For the denominator, that's another perfect, or not perfect square, sorry, difference of squares. So that's going to be x minus 3, x plus 3. The numbers that I cannot equal are 3 and -3. Got it. Writing this in lowest terms, I see that the x plus 3's can go. So now I have -3 over x minus 3. For the vertical asymptote, we get x equals, that was +3, so the -3 right here got removed. 3. As far as the gap is concerned, there is a gap, and that happens at -3 for x plus some y value. Now, for the intercepts, I have y doing this one. I substitute it in. I have -3 over 0 minus 3. That gives me -3 over -3, which is 1. 0, 1. Now for the x-intercept, we have to look at the numerator. Well, that gives me -3, and setting it equal to 0. That is a false statement. Since that's false, that means there is no x-intercept. And you just have to put none. And that's it. Those are the only two special situations that you might run into. You don't have an x-intercept because you have a number equals 0, or for the y-intercept, you can have a gap or a vertical asymptote. That one's a little bit easier to spot. All right, so that was quite a bit. There are several properties for rational functions, and that's not even all of them. I do have 2 more to go over with you next time. But hopefully you feel comfortable with finding the domain. That's factoring it and setting the denominator not equal to 0 and solving. Writing it in lowest terms, that's reducing by canceling out factors. Finding vertical asymptotes, those are invisible fences that break our graph. They happen at values that break the lowest terms. Finding a gap, those are removed x values. Finding the y-intercept where we cross, or finding the x-intercepts where we cross the x-axis. If you have any questions about this, please feel free to contact me. I'm always happy to help you out. But other than that, have a great rest of your day.